Let us now use what we've learned about limits and sequences to evaluate this particular limit without using L'Hopital's rule in calculus. Let me just write down the limit again. We call that L for this example. We attempt to find the limit as n approaches infinity for the sequence a to the n over n to the k. We have two constants a and k, and a is a constant greater than 1, and k is a positive number. Both are real numbers. Now to evaluate this limit, I will go through 3 steps. First is I'm going to make a guess. And for this limit, my guess is that it approaches infinity, and the reason for that is as follows. If we look at the denominator, we can see that there are k factors, and in the numerator there are n factors. And so, as n approaches infinity, there becomes many more factors in the numerator than there are in the denominator. And so the value of the numerator becomes much bigger than that of the denominator. And if the numerator is much bigger than the denominator, then we are approaching infinity. And that's why my guess is that this limit approaches infinity. And because that is my guess, what I'm going to do next is I'm going to find an easier and smaller sequence. So I'm going to say that again. I'm going to try to find a smaller sequence. By that I mean that the terms of this sequence are always smaller than this sequence here, and that it is easier to evaluate. And the reason for that is because the third step would be to show that the smaller sequence approaches infinity. So I'm going to look for a sequence that is smaller. So I have a new sequence here. Smaller. Then I'm going to show that this sequence actually approaches infinity. And if this smaller sequence actually approaches infinity, because this left-hand side is greater than the right-hand side, which is infinity, then this left-hand side must also be infinity. And so we've confirmed our guess if we've made these 3 steps. So now we've already shown the first step. I'm going to the next step. So the next step is to find a smaller sequence. And if we write it again, just going to write that again. We can make a smaller sequence by doing 2 things. First, we make a sequence with a smaller numerator. So this sequence will be greater if we make a smaller numerator, and we make a larger denominator. So the denominator is an easy task because n to the k here is a real number greater than 0, any positive real number. If we actually make the denominator into n to the k plus 1, then this expression is always greater than n to the k because both of them are positive, k and k plus 1. And in fact, just to make it easier for us, we're going to choose the greatest integer function of k plus 1, or let's just define L to be the greatest integer between the greatest integer function of k plus 1. So what this means is that it rounds it down. Okay, so Let me just write that again. So for example, if you have k equals 1.48, then k plus 1 equals 1. Or rather 2.48, then your greatest integer function k plus 1 floor is just 2. So it just takes the integer. It rounds it down. It doesn't matter what goes in the decimal part. So even if you had like 9.9, that will just become 9. So that's just taking the integer bit and rounding it down. And so we define L to be that. And so we can say that n to the k is almost, it's not almost, but is always less than n to the L. So again, let's write that. So now we already have a larger denominator. Now we just need a smaller numerator. And the trick I like to use when looking for a smaller term is to express that term in terms of its binomial expansion. So because I know that a is greater than 1, I can represent it as 1 plus some positive number b. So b is greater than 0. It's a positive number. And so its binomial expansion, the binomial expansion of a to the n is just 1 plus b to the n, and it will have many terms, right? And now I want to find, so this is the original term. Now I want to find something that is smaller. So to find something that is smaller, I know that all the terms in this binomial expansion are positive. And if I want something smaller, I just pick one term. One term from any, from all the terms. So, for example, I'm just going to pick the L plus first term. We are guaranteed that that L plus first term is less than the sum of all the terms, because it's just one term. In fact, L plus first term is included in this sum, and they're all positive. So I'm now guaranteed that my numerator will be smaller than a to the n. So I'm just going to pick the L plus first term, and I can actually write that down using the binomial theorem. And so that becomes b L plus 1 factorial L minus 1 factorial. So this will be my numerator, and this is smaller. I'm guaranteed that this is smaller than a to the n. And this will be my denominator, and I'm guaranteed that this is larger than n to the k. And so I can find now a new sequence that is smaller than this. And if you just write that again, the numerator is and the denominator now we can simplify that a bit. And we see that the numerator has L plus 1 terms. In the denominator, we only have L terms. And so if we write this as a factor, in factored form, we get and this is what we obtain. And then we use the product rule for limits. This is a constant. If you remember that's a constant, what we get is And this is a very convenient form because here we have a constant, and here we know that this limit actually goes to 1 because this bit here, the limit of this is 0, and the same is the limit here. So this is just 1, 1, and we have all the limits in between is 1, and we only have the last bit as a divergent limit, and this is infinity. So we have a constant times 1, 1, 1, 1, and there are L terms that are 1. And so if I just rewrite that, and so what we have is a limit that goes to infinity. And our limit L must be greater than infinity, and therefore L also approaches infinity. And there you have it.